the researchers are measuring?
No.
So,
I did not.
yeah. So remember, another way to identify the response variable is the explanatory is what the researchers change. Those are the treatments or the tied to the treatments. The response variable is what they measure as a response to the explanatory, right? So if it's a measurement from the researchers, that's a good way to identify response as well. Thank you. Yesterday, third block, Jeremiah volunteered to talk about his Hero Friday. Was it going to be LeBron? Is that what you said? So LeBron is going to be his hero, so I'm excited to find out why. Is anybody willing to share about their hero in here tomorrow? Say again? You want to talk about him, why he might be your hero? I mean, it sounds like you got a hero to talk about, right? Marcus, did you figure out your hero yet? Keep thinking on it. There's got to be somebody. An artist, a family member, sports player. Come on, talk about LeBron yet tomorrow. Why are you scared? Break the ice. Huh? It's kind of funny. Okay. Well, we would love for someone to tell us by the end of class that they're doing Hero Friday.
Come on, guys. I don't know about you. Somebody do it. Alright, so today we're going to be finishing up describing distributions, finishing up that mathematic activity. We all got our data collected in here, right? Yeah. Everybody rolled the dice through the pennies, all that jazz.
Oh, don't you put
Oh, yeah.
I got you.
Did everybody who rolled dice, not die, do the sum of 2 and the sum of 3? Okay, good. Then we're going to do normal distributions again. It's the name of the day, normal distributions. So same thing as yesterday, you can recognize normal, not normal distributions, but new thing, you're going to be able to interpret the mean and standard deviation in context. Keep that word in context in your mind. Alright, can everybody go ahead and get out that mathematic activity we did yesterday? It's a packet of 3, you don't have it. Your Frere models are in it too. I recommend having those out as well.
Can I go ahead and put this right here since you don't really need that space?
Yeah. So, I'm going to try to whisper, but your voice echoes really loud. If you guys have your data from rolling 2 and 3, or you didn't put all of your data up yesterday, go ahead and put your dots up. I know nobody did put up their sum of 2 and 3, because I didn't have these up yesterday. So, if you guys would like, go ahead, stand up, get moving, put some dots up on these graphs.
Yeah, I got a text Brad to figure out where to put that. Here's the dot. Here's the dot. Here's the dot. Here's the dot. Here's another dot.
Yeah, those are your Frere models for your notes and stuff. We're going to go back over everything. So you tell a little bit about it and you can have some notes right down, or somebody in your group has some. you're doing the sum of when you rolled 2 and the sum of when you rolled 3. Taj, did you get your points up? From sum of 2 and sum of 3? Did you get your points up?
I'm just gonna knock my water bottle to the ground like that. And then,
Alright, as we're getting those last points up, did we already talk about yesterday what these distributions kind of look like, how we describe them? We did? Okay, so can anybody tell me what the two big things are, or what the definition is for having a normal distribution? What does it have to have? Unimodal and symmetrical, right? Those two things, we have to have them. What if it's only symmetric? Is it normal? What about if it's only unimodal? Is it normal? No? Alright. So, we talked about yesterday, pennies. What does it look a little like? When we sketched the bimodal, right? It was supposed to be, according to the activity, it was supposed to be right skewed. Could have been the way we set it up. Sometimes you get bad data, just happens. But it is bimodal, so it's not normal. It's not, yeah, whatever. Anyway, stopwatch, what does it kind of look like? Huh? What? Unimodal and symmetric, so it looks normal. It's approximately normal, right? Like we still have, over here in third block, we have like 4 below 4.5. We have a couple above 5.5 that aren't, but it's approximately normal. We can look at it and be like, that looks pretty good. So that's important to keep in mind that it's approximately normal. It's never going to be 1,000% normal unless it follows the empirical rule, which we're going to talk about, I think, tomorrow if we don't get there today. And then what about when we rolled one die? It was uniform, right? Here, it looks like 6 is a little higher than 1, but what's the probability of rolling a 1? What's the chance? 1/6. What about rolling a 2? 3? So it's even all the way through, right? You have the same chance of rolling a 1 as you do a 2, as you do a 3, and so on. So now we're going to look at when we rolled the sum. So we rolled 2, added them up.
Can I do one thing with that really quickly?
Yeah.
just, I was just gonna point this out. We realized yesterday that some people accidentally put dots here and here because when they meant to put them over here. So pretend like basically none of these exist. None of those exist. Those don't exist. that makes sense. This will help in a
Yeah.
second.
Does that make sense to you guys? Just imagine they're not there. So, if these dots didn't exist, weren't here, what does this kind of look like? Unimodal and symmetric. So what does it kind of look like? Normal, right? Looks approximately normal. Now what about the sum of 3? Huh? Bimodal. What are we talking about right here, maybe? So, I have a question for you. We think this is bimodal. What do you do? What was the procedure for finding the sum of 2 dice? Yeah, you rolled 2, you added them up. What's the procedure for the sum of 3 dice? Is there a huge difference between what you did here and what you did here? Right, you just have 1 extra dice. But it's still the same procedure, it's the same thing. Is there the same amount of randomness here as there is in rolling 2? Maybe a little more because you have an added die, but yeah, it's still completely random. With that in mind, what do we think this distribution is? It's not going to be uniform, right? Because you can see here we have 1 at 3 and like 15 at 14. Huh? Unimodal? Yeah, so there is this little part here, but for the most part it goes up and down. Looks like one big hump. What else could describe that distribution? You think it's skewed? So, what if, oh, I need this one. Bye. Does that help at all? Looks pretty symmetric. It's unimodal. We already said that. So what is it? Approximately normal. Crazy. What do you guys think would happen if we rolled 5 dice, added up the sum? What would that distribution look like?
You ready for me?
Yeah.
Okay.
Anybody else? I heard 1 normal. Does anybody think anything different? What if we rolled 20 dice? What would that distribution look like? Normal, right? Randomness is important for normal distributions. If it's normal, you have to have a certain amount of randomness, and when it comes to rolling dice and adding up the sum, it is always going to be completely random. Unless you rig one of the dice to fall on a certain side, dice are random. So, keep that in mind when talking about normal distributions or randomness. Mr. Kennedy's going to show you a cool calculator.
And so one thing I do want to, if you can just pull down the screen. Actually, I can do it. Okay, so sorry. Before that, I forgot something.
Oh, no fault.
No, you're good. I told you the wrong thing to do. Alright, one real quick thing, because I will say this. Y'all talked about this being unimodal and symmetric. So one thing that happens when you actually play with this and get it right. So, do we have infinitely many data points? No. Sean's looking like, that's not even possible, Mr. Kinney. And I'm like, yeah, that's fair. But I can do a whole lot more data points, right? If I did a whole lot more data points, this graph would look more like this. And you can kind of see it. It kind of looks like a V, doesn't it? Like, notice I did that in there. Similar thing in here. So we've done like a smooth curve for this. And if we did more data points, we would get more here in the center. Because if you roll a die, a single die, right? What is roughly, do you think, the average number that you would roll? Notice the average, not the typical, because we get the same all the way through. But what would be roughly the average for a single die? 2 or 3? So like, you think the average would be here? Between 3 and 4? Notice when we say average, we mean the middle, right? So if I have one die, the average would be about 3.5. And so each die would have an average of about 3.5, right? So 3.5 plus 3.5 plus 3.5 would be about 10.5. So if I have 3 dice, it should be somewhere in here is kind of my peak, is what's going to happen. So let's look to see what happens digitally. Because here's the thing, do y'all really want to go all the way out to rolling 20 dice each and doing it 6 times and counting it all up? No, see, this is why we love technology, right? We can do simulations for this. And so at the end of the day, when we talk about a die and we roll it, there's an R word to describe the outcome. It's random, right? Have we used a calculator to do random stuff before?
Yeah.
We sure have, right? So calculators are random. So I'm going to type in equals rand integer, so rand int, and I'm going to roll something between 1 and 6. And don't worry about the mismatch, it'll fix itself later. So there it is. And so what I can actually do is I can just drag this across and notice how it did 4 random numbers. And so it may look like it's not random, but I promise it is. And so what I did is I set up a formula here to add all those numbers together. Now, because I have technology, I can drag and drop again. And how many data points do you think I should have? How many sums?
300 is enough.
300 is enough?
Now go 400.
Go with 400?
500 maybe.
500 maybe?
Does it go to 6?
Does it go to 6?
What about 7?
Could I make it all the way 700? It could go to what? It could go to infinity. Do I want to go to infinity? And actually, I don't know if a computer like this could go to infinity. I'm just going to go to a little bit more than 1,000. And I say that because I'm just going to stop when I see them at 1,000. But I may go a little past. So, yeah, so we're looking a little past 1,000 here. Whoops, 1,035. So notice we got all those sums there. And so we went from a uniform distribution to a V-shaped distribution to something that's a little bit more normal. What do you think it's going to look like when I do a sum of 4 dice? Normal? More normal maybe? Okay? So I'm going to come down to here. And so I actually already had it built. I should have deleted this. So I can remove this variable. I should have already done that. And it looks like, woo! You know how many data points are just floating in space right here? About 1,000, 1,035. So I add my variable in, sum 4, and notice it has a dot plot in there. Man, what does that kind of look like? It kind of looks like a mountain. Come on, we can use better language than a mountain. What's the statistical terms we've learned with this? It's what? Unimodal. Andrian, it's unimodal. Is there anything else we could use to describe this distribution? Symmetrical. So Deshaun, since you already said symmetrical, I'm going to guess you know the next part of it. What can we call it if it's unimodal and symmetrical? Approximately normal. Notice I do say approximately. It's not perfectly normal, but it is approximately normal. Cool, 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 cool. So I'm going to jump down here. I'm going to delete this sum really quickly so that we don't see it when I come down here. All right. So now I have die 5, and so I'm just going to do the same thing. Equals rand integer 1 to 6. And you'll notice it says error here because I have a sum with that 5th die, but I don't have a 5th die yet. But let's copy and paste it. How many times do I got to do this? 1,035 times. Do I really want to do that by hand? Hard no. But is it easy enough in a calculator using technology? 100%, right? And so I know you have to wait a few seconds. I apologize, but we'll get there in just a minute. While I'm getting there, any predictions about what this is going to look like, Zai? Any predictions what the graph of this is going to look like? Any guesses?
Nothing. Sort of like the same.
Sort of like the same? So meaning what, Jaden, if it's sort of like the same? Might look, say it louder? Maybe normal? Let's find out. Sum 5. Oh dang, that does kind of look what? A little steeper, but still approximately what? Normal. I'm going to change it to a histogram. Ooh, that's even better. That's even better, right? Nice and symmetrical here. Comes back down. By the way, what did we say the average roll per die would be? 3.5. And you know what happens when I do 3.5 times 5? I get 17.5. Man, what's right in the middle here?
18.
Oh. So it's 17 to 19, so about 18. So, yeah. Notice that average isn't changing. Cool. Alright, so let's do one more. Caleb, I'm about to jump from 5 dice to 10 dice. I'm going to do a sum of 10 dice. Any predictions what that graph is going to look like when I do 10 dice up here? Kayla's here, isn't she? Okay, what? You don't think it's going to be normal anymore? Why not? You just think because I'm asking it's going to change? So let me ask you this, and I want y'all to hold on to this for the rest of this year. Marcus, we started out with a distribution that was, what was it when it was kind of like this, flat across? When we did one die, what was the shape of that curve or distribution?
You want me to say like the math word or like?
Yeah, that
just like-
statistical word, the word we are trying to learn. Alright,
I got you in 3 business days.
I got you in 20 seconds. Taj, do you remember what it was? Say it louder. Uniform, because like if everyone wears the same thing to school, you are wearing a what? Uniform, right? It is uniform across. So, Marcus, what's it called, that first die when it was all the same?
A uniform?
Oh, uniform distribution, there we go, right? Not 3 business days, 20 seconds. Alright, so then we went to the 2 dice and it kind of made a what? A V shape, right? Andriana, you with me? KJ, you with me? Alright? And then we got to the sum of 3 dice and it became more what? It rounded out more, became more... Yes? There's an N word that's kind of important that we said every time so far. Oh, say it again. Did it become more normal? And then we did 4 dice and it became more... normal, and then we did 5 dice and it became more normal. So, Kayla, why would that pattern change? And I want y'all to hold on to this. I want you to think about it. We're going to see it in a second. But math is logical. Even a lot of statistics is logical. If you see a pattern, unless you see evidence to break from that pattern, don't break from it. So I want you to think about that, right? There's a pretty solid pattern that it keeps becoming more and more normal. So Kayla, what do you think is going to happen when we go to 10 dice? What would be logical? Normal? Let's find out, right? Don't be afraid to make predictions, but I do want us to think about that, like, there's no evidence that things are going to change. So let's keep along that line, just for a thought process. Okay, so equals rand, integer, 1 to 6, enter. Yes, I know there's a dimension mismatch. Boop. I know there's a dimension mismatch. Alright, now let's drag these 5 dice all the way to what sample size again? 1035. Oh, that's so much. We got this. Could you imagine rolling 10 dice 1,035 times? No, I love technology, man. How long do you think it would take to do 1,035 rolls?
4 to 5 days.
4 to 5 days. A long time, right? Alright, let's look at it. Sum 10. Huh. There's this weird gap right here. Or not gap, it kind of dips down a little bit. But overall, I don't know why that would happen. Actually, I do know why. I'll explain why in a second. But overall, if we ignore that, let's say I change this back to using a histogram. Notice histogram is just a bar, set of bars. Notice it still looks approximately what? Normal. Okay? So, did it change to bimodal? Or something different? No? The pattern, it stayed. Okay? And so I want us to start to notice this. And so hold on to these ideas. The reason, by the way, that it dipped back down a little bit, a big reason is because these rolls were what? Random. In the real world, like, randomness introduces this idea that things can act different than we might expect sometimes. Okay? Now, I do want you to think about it, because we're going to now look at the mean and standard deviation. Is that right? If we have 10 rolls, anyone have a prediction what we would expect the mean of all 10 rolls or the sum of those 10 rolls to be? Just want you to think about it. How about we do this? Take 30 seconds, talk to your small group so that we all have ideas from each other. So Andriana, we gotta get our head up. KJ, I need our head up. I need y'all talking. Jordan, I need y'all talking. So, Jack, so I want you to just make a prediction. What do you think the average for those sum of 10 rolls might be?
One dice.
Well, it's 10 dice, and we're adding up those 10 dice. So what do we think the average might be if we're adding up 10 dice? So don't pull it till you got it. So I definitely heard some ideas from the front. Jaden, what'd your group come up with? Michaela? Huh? Say again? You think the average is going to be 5? Okay. Okay, what was our reasoning for that? So 5 is the middle of 10. Okay, okay. Bree, what'd y'all come up with? Y'all come up with anything? Taj? Y'all thinking 35. You know, I heard that from y'all as well. Why were y'all thinking 35?
Because the average is 3.5, and when you got 10 dies, so you take 3.5 times 10,
So we said each die we expect to see roughly what?
3.5.
3.5. And Jaden's like, oh, that makes sense. So y'all were thinking 5 because you were thinking of the 10 dice, right? But each die has an average roll of what? 3.5. By the way, if you look right here, right here in the middle, what number is that? 34. What number is that? And what's right in the middle of that?
35.
Oh, maybe a 35, right? But I want y'all to hear me something. Bad predictions are, actually, predictions that are wrong are not bad predictions. That's the way I should say that. Predictions that are wrong means that you thought in the first place and that's true. Okay? So I want to encourage us and think about that. Do you want me to go ahead and do the calculations real quick? Sure. Was there something before that in the slides?
I don't think so.
Okay.
The real world stuff.
Do you want to talk about those real world examples before we start talking about mean or median, or do the mean and median, or mean and standard deviation, and then go to the real world and let them practice with that? It's your choice. I'm flexible.
This is already done, so just.
Okay. All right, cool. Sorry for that short intermission. All right, so here's what we're going to do. Again, I love technology. It's awesome. So with this piece of technology, what I can actually do is I can go over to the side here, and I can get the technology to calculate what are known as mean and standard deviation. What do I mean by mean?
What's
The average? Okay, so what do we mean by average? Kayla, do you remember what we mean by average? Okay, so we need to know this, right? I know you know this. It's somewhere deep in there. We got to know this. Like we got to hear the word average. We got to know exactly what it is. Mason, what do you remember about that word average? We've even done it in this class earlier this semester. Or you don't remember using average earlier? Are you asking what time it is, Deshaun?
Yeah.
It's right there on the clock. I fixed it. Let me ask this, before I tell you what average is or mean is, does anyone remember what activity we did where we used the average? So stopwatch, we just graphed how long it took. It was actually a couple weeks ago when we were looking at study design and bias. There was something with average. Say again, Andrea?
The song lyrics?
Oh yeah, you remember we looked at the song lyrics?
Oh, yeah.
And we took each of those words and we found out how long each word was, and we found the average of those. So what did we do, Mason, if we were finding the average of those song lyrics, the words? But how did we find the average? I'm trying to, so like we did look at 5 words, we did 3 different samples with it, but like how did we actually find that average? What did that mean? So you took all the length of each word, you added them all up, and then you divided by how many words you had, right? That's how we calculate. Ms. Kowalski's about to go into what does that number actually mean. But how many data points did I have here again? Not just a bunch. Come on. Over 1,000, right? Do you want to add up 1,000 numbers and divide by 1,000? No, that sounds like a hard pass, right? Y'all haven't even learned of something called standard deviation. And standard deviation's not bad, but it takes a lot of steps to get there, so we definitely don't want to do that by hand. But on these calculators, technology is a beautiful thing. I know some teachers are like, ooh, AI, blah, blah, blah. No, dude, technology is the best thing ever because it helps make our job easier if we learn how to use it the right way. Hear me on that again. As long as you're still thinking with it and staying awake in class, right, Tyler? Technology is completely fine and good. All right, so I need sum 10. There we go. And I'm going to put, I think that's Mel, it in the first column. Boop. All right, there we go. Does anybody know where the mean is in this column over here? Anyone see the symbol for mean? There's a whole bunch of stuff you don't really need. But say again. X with a line over it is what you're thinking. Adriana, what are you thinking?
The one by 36.
The one by this one right here? 36,147?
No.
This
Right
one?
there on the other side.
Right here? So what do you think MIN, anyone know what that might, minimum? So the minimum sum was 19. Does that make sense? Okay.
I mean, median is right there about 35,
So median is 35.
but you got to also, with the X line over is 34.9.
That X with the line over it is 34.9. What did we say we expected the mean to be? 35, right? This symbol right here means mean. That's what that symbol means. It means mean. Okay? So if you ever see X bar, that's how you read it. It just means mean. That is actually why, because I started teaching statistics, so I got that poster right there to help you remember it, hopefully. I hear he is really what? Mean. And what's that symbol up there? It's the mean, right? Like it's a nice, fun stats joke. Hopefully that'll help you remember it. So I hear he is really mean. It's literally the mean symbol, right? Or average. All right. Ms. Kowalski, you ready to take over and talk about how to interpret?
Yeah.
Okay. And then there's this thing called standard deviation right here. But Ms. Kowalski's going to talk mostly about how to interpret these numbers. And I need y'all to pay attention to this. The ability to know what mean is, know what standard deviation is, you need to know those terms for your proficiency scale, but you also need to know how to interpret those. We're not going to go through all the calculations. On assessments, I will give you the mean and the standard deviation. I'm just going to ask you to interpret it, okay? So as long as you can interpret it, that's all I need out of you to understand what they mean. Or did you want to just use this to start? And then take them, what I was thinking is we use this as a setup for the real world context, and then that's what I was thinking. Yeah.
Okay, guys, so we already established this is our mean and this is our standard deviation. So I want to be broad with this question, and it's supposed to make you think, so give me whatever answer comes into your head, okay? What is this mean saying? Okay, it's the average, right? That is what the mean is. But in the context of this simulation we just did, what is the mean? So what is context? Like, do you know what?
The average of the dice.
The average of what dice?
The 10 dice, 7.
Yes. Okay, so the mean is the average Sum of the 10 dice we rolled. Sum of 10 dice. Right? Does that kind of make sense? Using it in context, that's what the mean means. It means the average sum of 10 dice was, yeah, so the average sum of the 10 dice we rolled. Now, standard deviation, let's break down that first. So, what does standard mean? Normal. Any other word we can think to describe standard? Regular. Anything else? Somebody besides Sean want to give me a synonym for normal or regular? I like what? Average. Basic. I like to use the word typical. Like the typical is the standard. And then deviation. Do we know what deviate means? Different. So if I tell you, I want you to walk to the end of the room, take a right, and walk to that wall. And you walk to the end of the room and take a left. You're deviating. You're not following the path. You're changing, right? You're changing what I told you to do. So I like to use change here. Charge, change. So the standard deviation is the typical change. What do you think is the typical change from? The average. It's the typical change from the mean. So in the context of this problem, if our standard deviation is 5.501, how are we going to say that in context? So let's break it down, okay? What are we talking about? The what? The sum. So let's start with that. The sum of the 10 dice, sorry. I'm not very good with English. Okay. The sum of the 10 dice, and what are we talking about here? What are we trying to put in context? The typical change, right? So the sum of the 10 dice, so you want to maybe put in there typically, because we're talking about the change. That's what I'm going to give you. I'm going to say the sum of the 10 dice typically changes what? 5.501 what? What is it changing from? What is happening? Oh, it can go higher or lower. It can go either way with standard deviation. But what is this referencing? What is the standard deviation attached to? It's the typical change of what? So what is the sum of the 10 dice typically changing 5.501 from? Yeah, typically changes 5.501 from the mean of, I'm not going to rewrite this big number, but from the mean of that. That's all we're looking for here, putting it in context. Does that make a little bit of sense? I would recommend on your Frere models you guys got yesterday, writing down what standard deviation is. There's going to be a more formal definition in a minute, but if this is helpful for you to see the breakdown of standard and then deviation, I would write that down.
I would also point out that quite literally, the interpretation just goes back to that definition. It's a typical change. I would add typical change from the what? Mean, right? So that, yeah, I saw it there. I just meant like, we didn't write it over in the definition part, but I would include that detail So it's typical change from the mean. That's it, and then you put the context with it. Yes, Scott?
I'll leave that up. Okay. Hey, Brandon, can you help me send the Jack out? Yeah. Oh,
What's
do you
that?
have your button today?
I couldn't find it. I thought I put it in my new backpack.
Okay.
Sorry.
Thank
I'm gonna
you.
keep looking for it though.
Alright, so that is standard deviation. That's how we interpret mean and standard deviation into the context of a problem. So I have a couple examples up here of how this applies to you, how this applies to the world. So the first one, not so fun, distribution of ACT scores. So when this says the mean, this is approximately normal, right? We can kind of see that. When it says the mean is 21 and the standard deviation of about 5, what does that mean? What does that tell me? If we're talking about the distribution of ACT scores, how are we going to interpret that? How are we going to put that into context? So what's the mean? Definition of the mean. The average, okay. So the mean of the distribution of ACT scores is 21. What does that tell me? Right, so the average ACT score is 21, and then the standard deviation is about 5. So average ACT is about, ACT score, about 21. What is that standard deviation of 5 telling me? It changes. You're there. You got it. So the average ACT score is about 21 and typically changes what? 5 from the mean. Does that make sense? We're literally pulling the definition, putting them together in the context of the problem. Okay? So, same thing for, this was my favorite one I pulled. It is the distribution of NFL player retirement age. Crazy, it's approximately normal. And the mean is 33 years and the standard deviation is about 2 years. So what is that? Let's interpret that. Okay, the average age of retirement is 33 years. Years what? Okay. NFL retirement. Retired is 33 years old. And
Can we let them do standard deviation of that and the last one on vertical surfaces
oh yeah,
before we talk about it?
let's do that. I look a little tired today. So finish this out by talking about what the standard deviation is, interpreting that, and then this last one is the distribution of male height. I can write it down on your vertical surface if you're not able to see it that well. But everybody up and go to your vertical surface with your group. No, yeah. I was trying to figure out if we could do something like that today.
They also need practice doing it individually / in small groups. What's up?
But no, I was trying to. Yeah, you guys right there.
So, the standard deviation, if I remember correctly, is about 2 years. Okay.
The standard
What
deviation
is
is
it?
2 years
Don't
on
use
this.
it.
Okay, and then, can you see the next one? Of what it's talking
Y'all
about?
talk about it.
Okay, I was gonna make sure y'all can see, so you're not like going in blind here.
What's the word said after that?
Huh?
What's the word? After that, I can't see it.
Retirement. I just shortened it, so. Alright guys, what are we thinking? You guys have a name. You get I already have the first part of the sentence for now for you. Just gotta fill in the rest. We're interpreting the standard deviation for the rest of this, and then interpreting the mean and standard deviation of this data.
And then what about the average?
There's something back to how we put that together there, use the resources, talk with each other. You get over there? Are they talking to you? Are we sharing ideas? Okay. I mean, you tell me if it's right. But, are you confident?
Yeah, 2 cents.
Okay. Come on, Forrest. You guys got it. Talk with each other. Look back at that first example we have right there. Right next to it. What is that saying, and how can you interpret the next one? Hey guys, real quick, I do want to point out, I see a lot of writing and not a lot of talking. Which means one person in a group is writing down what they think is right. And that's not the point here. The point is to talk to each other and share ideas and get something going. So I don't want just one person writing on the board. If you have the answer and you want to write that down, you give the marker to, or chalk to another group member so they can participate in this. Share your ideas with them.
I need some more.
What? Huh?
It's something
He said what's the SD?
SD is standard deviation. And SD is an abbreviation for standard deviation. If anybody
We know our three, like,
we do the first one together, just do the last two.
Like you said earlier, she told you to walk this way. Walk that way. But you, that one said it. Let's do it. That will change it. You change the average. That baby done.
Can you guys see the next one? It's talking about male height. the mean is 70 inches and the standard deviation is 3 inches. And it's just talking about male height. The last one. You guys finished?
I spelled change wrong.
What'd you say? You said man, each of them.
Standard deviation of about 3 inches.
So, one question. Is the standard deviation plus or minus 3?
Yeah, it goes up and down. It's not just one
That
way.
makes
So
sense.
the last one about man's height?
Yeah, male height.
So if I can write that standard plus or minus 2.
So if it was calculated the way standard deviation is calculated, yes, that would be standard deviation. It is very, we're not gonna go over the formula, it's a very complex formula. We don't. Does it change to 3 inches? Does it change to 2 years?
It changes 2 inches from
What do you mean? What do you mean? What do you mean? I'm confused on what you mean. Like, are you saying the retirement can go from 33 years old to 2 years old? What do you mean you flipped it? So what is the standard deviation?
Wait, I'm stuck. Why are you looking at me?
What's the standard deviation?
Oh.
No,
Average
like
male
what's the
height
definition of standard
is-
deviation?
You don't even say about,
Typical change
you can just say
from-
70 inches, or the typical male height 70 inches. And typically changes.
So, this,
Typically
it's not
changes
saying that
from-
you're going, you retire at 33 and then you retire at 2. Or you retire at 2 and
Same
then you
idea,
retire
right?
at
They
3.
just, and typically
It's
changes
saying that,
from the mean.
so the one standard deviation away would be
That typical
35
change is
years
gonna be
old
really important
or
for the next
31 years. So it gives you that range to go down by. Does that make sense? How that breaks it up? So what do you need to add in here to make it make sense? Hey Mason, I'm sure you're with the 9s, not the 8s. We're gonna get together and talk in a minute. Alright guys, let's come to the middle. Let's get together.
I need to wait.
Alright, so let's talk about this. What were we all thinking? Somebody from their group give me what they came up with. Huh? For the second one, what did we come up with at the end?
Back in the typical change. In 2 years, the typical change of 33.
What do you mean by 2 years of 33?
Like of the average of retirement.
Okay. So, the age of NFL retirement is 33 years old and the typical change is 2 years of 33. Can anybody think of a way we can reword that to make it a little more concise? Or a little more,
Context.
yeah, a little more in context. Yeah.
Typical change is 2 years of the mean.
Of the mean,
Of 33.
huh?
Of the mean of 33.
Of the mean of 33. So I would, personally thinking about it, instead of saying of, from, right? Because we ran into an issue, don't remember what group it was, we ran into an issue of, okay, we're changing from 33 years old to 2 years old. Do we think people are retiring from the NFL at 2 years old?
No.
Right. So we're not changing from this number 33 to go all the way down to 2 or to go all the way, well, that's the only way it would go, all the way down to 2. We are saying that the typical amount of variation from the mean is about 2 years. So, one standard deviation away, the typical amount of people are retiring is either 35 or 31, right? You add up or you subtract down. So, the way I would word that is The average age of NFL retirement age is 33 years old and typically changes about 2 years from the mean of 33 years old, right? So now we're going on to male height. Let's see. The average male height is about 70 inches and typically changes about 3 inches from the mean. Yep, that's spot on. Literally take our definitions we constructed and mash them together. All right? Make sense? Give me a yay or nay if we're catching on or not.
Nay.
Not catching on? What are we confused about? Tell me. Help me help you. What are we?
See, I wasn't expecting to have to explain myself.
Okay, well, I want to help you. So if there's anything you're confused on, please ask me. Is anybody specifically stuck on one thing that you're like, you are making no sense right now, Miss Kay? We're good? Okay.
Wait, can you explain standard deviation real quick?
Explain standard deviation? Okay, so I don't want to give you guys this long formula, how it's calculated. That's difficult. But, so what we're saying is when we have our distribution, and I'm going to use the NFL retirement of 33. Standard deviation is going to make a lot more sense tomorrow when we get into empirical rule, because you'll see, okay, this is how the standard deviation ties into the amount of people, the typical amount. So what standard deviation is saying is typically with NFL retirement, people are retiring about 2 years away from the mean. So people will retire at 35 or at 31, right? Right? I did that right. Plus 2 minus 2. So that is the typical amount of deviation, variation, change from the mean is 2 years. That is 1 standard deviation away from the mean. Okay? Does that make a little more sense of how that looks?
Can I just add
Yeah.
one thing to it? So I know we don't really want to get a lot into the formula, but so we said deviation is how far away it is, right? How would I mathematically calculate how far away something is? Well, is it add or is it going to be subtract? It's going to subtract, right? So in this problem here, we had a mean of, let's just go ahead and round it 34.9. We good with that? So when I look at this, I think that's 33. 33 minus 34.9 is negative 1.9. That's a deviation. That's how far that number is from the mean. This one is 32 minus 34.9, and that is equal to what? Negative 2.9. That's how far that number is away from the mean. There's one here that's 20. I'm going to use this 40. The 40 minus 34.9 is 5.1 away. So notice how I'm calculating these deviations. Literally how far that number is from the mean. Okay? This number right here essentially is telling me what the average amount of deviations is. So like if I were to look at all of these deviations, what is a typical amount of deviations? It's almost like an average of all those deviations. That's a good way to think about it. So when we say standard deviation, so these are my deviations. They're how far from the mean. These are just examples. So deviations from mean. So when we say standard deviation, we are essentially looking at the average, which is what is typical. We're essentially looking at the average amount of deviation. So when I look at the deviations of all of my numbers, about how far are they from the mean on average? 5.5, right. Does that help put that into some context to see it? So it's just looking at those actual deviations. Okay, how far are those deviations in general? That's all we're asking for standard deviation. Marcus, you were the one asking that question, right, for clarification? Oh, no, who was it?
Taj.
Taj, does that help clarify it? Okay, so just think about those deviations, that's it. And once again, like, go back to the words carry meaning. I want us to understand that. I hope that's something we get throughout this course. I know a lot of other classes don't seem to focus a ton on vocabulary, but vocabulary carries weight. If we understand what the words mean, deviations, standard deviations, like those words carry meaning, so focus on the meaning of those words, okay? Are we getting to empirical rule now? Isn't that what's next? Or is it the rule more, is
There
that
is-
IQ stuff? You have the remote, you started the next one,
Yeah,
yeah.
but it's,
Oh, that's not on the slide, so you can't
No.
do that.
I was gonna see, but.
There you go.
Okay,
You want me to erase this up here?
yeah. Do you guys promise not to fall asleep on me?
Jack can't promise that, but
Yeah.
Jack's trying to fall asleep standing up right now.
I think we're gonna stand up for a couple more minutes, just to wake up a little bit. We're already up, might as well keep standing.
Can-
Jack said he
Can I
was
do, since I'm already up here, can I talk about these two really quickly?
Yeah.
Okay, so. There we go. And there we go. I want you to notice these two distributions have roughly the same mean. It's just the center, right? Which of those has a higher standard deviation? You think this one has a higher standard deviation? Why not? Okay, so you're now thinking higher point means lower change. Okay, there's something else with it. Keep thinking. Jack, what are you thinking? The lower one down here, why are you thinking that one?
It's more spread out.
So remember, so one word that we always talk about in statistics for standard deviation is how spread out it is. Which one is spread out more from the mean? So this one is more spread out. So higher standard deviation. More spread out. What's actually I shorthanded that a lot. What's a key word I should probably add in there? More spread out from the mean, right? So that's what we always want to remember is spread from mean. So spread out from mean, so higher standard deviation. Less spread out. From mean, so less standard deviation, or lower standard deviation. Ms. Kolsky, that's all you wanted on this, right?
Yeah.
Do we want to give them a few minutes to take notes on standard deviation? So, add this stuff into your notes. Y'all have a Frere model, I believe, on standard deviation. No. So add these notes to the normal versus non-normal distributions. Add in information about mean and standard deviation. Ms. Kolsky, if there's any like defining things you want to write on the board, go for it so they have it to write down.
They wrote down earlier, right?
Oh, did they?
Yeah.
For mean and standard deviation?
Yeah.
Okay.
I hope so.
Yes.
That's broken.
This one not taken.
The Frere model that says normal versus non-normal distributions on the front, that's the one I would use to make notes about mean and standard
A little bit
deviation.
fine.
Yeah, did you?
In the notes section, bottom left.
Yeah.
If you run out of room there, you can put it on the back side where there's the answer key as well.
then once y'all finish writing notes down, that, paper we're working on to record all our data, get that back out, because we're gonna work on the other side of that. It says, do you have 5 seconds? On the other side. So, you got it. Okay, good. I thought you were confused. Are we good to move on, or do y'all need a couple more? Like a minute more? Yeah. Alright, if you're not quite finished and somebody else in your group is, just look over on theirs real quick. To get the last little bit. We don't have that much time, and I really want to get into at least the start of this. So, everybody get out the, do you have 5 seconds? It's like the other side. Is that paper we're working on? So, in the stopwatch task, it's gone. It was over there. You guys remember you stop the stopwatch as close to 5 seconds as possible? You try to stop as close to 5 seconds as possible. Last year, the distribution of times for this task was approximately normal, with a mean of 5.02 seconds and a standard deviation of 10 seconds. SD. 0.10, sorry, not 10 seconds. I misspoke. 0.10 seconds. So, look at that in a minute. Do you guys see this little the graph they have labeled out? So, what is at 0 standard deviations? What value? Right in the middle. 5.02, right? Our mean is 0 standard deviations away from the mean. Does that make sense? There is 0 movement from the mean. It's our mean. So, rewrite that. What about 1 standard deviation away? The positive. We're going up. Huh? 6.02?
No, it's 6.12. No, 5.12.
Yeah, so it would be 5.02 plus 0.1. I misspoke earlier when I said 10 seconds, but it would be 5.12. Right, we're adding 0.10 to get 1 standard deviation away from the mean. So then we have 5.12. What about 1 standard deviation below the mean? Yeah. Yes. 4.92. What about 2 standard deviations above the mean?
5.22.
What about 3 above?
Yeah.
What about 2 below?
4.82.
And what about 3 below?
4.72.
Okay, so you guys can write it on here, or you can fill it in here. What value is 1 standard deviation below the mean? Yeah, 4.92. What value is 1 standard deviation above the mean? Now, I want you guys, with your groups, I'll give you like a minute to talk about it. What percent of values do you think lies between 1 standard deviation? So from 4.92 to 5.12, how many of the stopwatch values do you think lies within here, like a percent? So like, if you think 20%, 1,000%, 27.3%, whatever you and your group are thinking, write that down. Huh? Yeah, out of it. So I want to make it clear, 100% is the whole thing.
You write it down?
Write what down? Like what you think?
Yeah.
Yeah. All right, what are we thinking, guys?
70-60%.
Yeah, you think 70 or 60%? Anybody else disagree with that? Think it's more? Think it's less?
50%.
You think 50%?
Yep.
All right. You think 84%? Okay. Now, what about 2 standard deviations?
What's in that whole middle part?
Yeah, so from here
Like
to here.
80 to 90?
You think 80 to 90? A little more? Anybody else? Think more? Think less? We all think it's 80 to 90%.
No.
What do you think? You think 60 something? Okay. 75-ish? Now what about 3 standard deviations? I want to make sure you guys see this. I want to make sure we're aware of this. So the 3 standard deviations isn't here, it's right here. So from there to there, what do we think? Huh?
So from the whole graph?
So they're like 100 of them.
Yes.
97.
Think 97% just about?
98 period, 98 period.
You think 98?
86.
86? Maybe probably a little more than 86. We're right on the edge here. So, I want to try to quickly show this to you guys. We're going to figure out what those actual percents are. We're going to go a little more in depth tomorrow. The graph.
And you're on all these variables.
Yeah, they're talking about. Have they interpreted? Oh, they just estimated.
Yeah, this is just estimating percents, and then you open the thing to see.
Yeah. How about, yeah, we got 2.5 minutes. How about we have them interpret mean and standard deviation, and they end there. They do it individually.
Okay. Not showing you guys the actual percents, leaving you on a cliffhanger there. Gonna have to figure that out tomorrow. But go ahead and interpret the mean and standard deviation in these contexts. So, 1 standard deviation away, 2, so on and so forth.
Because we need y'all to actually practice this, not put it away, Jordan, before you try it. Interpret the mean and standard deviation for the stopwatch task, or continue to put it away, because I don't care if you learn. Well, the standard deviation.
You can, yeah. It's really just for you, your estimate. We're gonna get the actual percents later. Huh? What is number 5?
0.02.
No, wait. No, so your estimates are here tomorrow. We're gonna use an outlet to like actually see what our real performance are.
You can always have it in this class. Hey, Jordan, what you doing right now?
Same thing we've been doing all day.
What you doing over there?
Every class I go to, every class I have, I was looking at all this.
What, say again?
I think we figured that out already.
If everybody can make sure to bring their iPad tomorrow,
Yes.
at least
And
one,
charge.
not at least one per group, you don't know what group you're gonna be in. So please bring your iPad charged tomorrow.
And who have we not gotten at TK?
I need to check it out, I know Jack Mason, I got Breeze, I got Sean. Taj, did I get your NTPA form?
Hey guys, if you do not have your NTPA form turned in yet, we need it tomorrow. And if you need an extra copy because you lost it, please come see Ms. Kowalski to get it. We need it. Please help her out.
Guys, I get a grade for this. If you don't give me
Not
your
just a
forms-
grade, they decide if
Yeah.
she can be a teacher next year based on what we do in the class, so we need that form.
Specifically your forms. I really need those. Yeah. Huh? You need them.
It wasn't even
Have a good rest of your day.
So we're starting with this today. We're doing that again though, interpreting. We're gonna go back over that.
Yeah.
We're gonna do that.
I don't think they fully finished it this year.
So we'll do the.
Head on over to, who do you have, Miss Granberry or Miss Williams? Remember, if you're with Miss Granberry, you're going down to the theater.
Theater? Oh, DJ, we're going to theater.
If you're with Miss Granberry, you're headed down to the theater.
You're there.
That's what happens when I don't try. Just like your hair grew.
Oh, thanks! What if I like just sit in the back and be like
No.
so quiet? You
Bye.
never know I'm here.
I'll get her
Bye.
I'll like hide like your cat.
I can guarantee you in the kindest ways possible, you can't sit back there and be quiet the whole time.
You sing it. Yes, I can be a good
DJ's like, nah.
I can be quiet. It's like,
But you
Can I stop?
won't be.
Can I step out and do on the way, or is that not allowed? Because I have to get my elbow pads. I left her.
You have to what?
I left my elbow pads up. Hey!
Yes, that's fine.
Perfect, thank you.
I forgot to, I have not scored these yet.
Where
It's
are
fine.
you going?
But I only got one person on these questions today. Can you quickly go and scan these so that I can use the digital scans to score them and then I can give those back to them? Actually, I say that. I need to go, I need to do, don't worry about that. What time's your interview?
3:30, mid
So you
of
got time.
planning, yeah. I'm gonna go through it because
Why
I
does it smell like fish food?
It always smells so bad. The forms put like a check on the
Yeah, and go ahead and do, just use a pencil and, put their actual collaboration source in today.
They went to the theater? We're going to the Christmas.
I have not finished, but that was
Oh, yeah, you
definitely
got,
one of your better BYUs.
Pencil?
No, y'all didn't see the.
I thought that was it.
I think I got all the like types of grades. Mr. Kid.
No, you just missed one of them.
I did? I only missed one?
Wait, how did I do?
Are you with Miss Williams?
Yeah,
Or-
I'm Miss Williams.
Then have Miss Williams, if you're with Miss Granberry, go to the theater.
So was one of them conditional There, frequency on this?
Yeah.
Okay, that makes sense.
Wait, how
'Cause-
much did I get wrong?